Welcome to your No Malarkey Guide to Programming. My name is Kalu. In the last video tutorials, we were able to use matplotlib pyplot to go ahead and plot a nice graphical representation, a coordinate plane that had a whole bunch of a scatter plot, pretty much, that had all of the data points representing each NBA player and their height. On the y-axis was the height, and on the x-axis was just each NBA player. It was player number 1, player number 2, player number 3, player number 504. And it was organized, it was arranged from shortest to tallest, with player number 1 on the x-axis being, what is his name? Nate Robinson. And player number 504 or 505, whatever number it is, the last player, the tallest player, being Hashim Thabit. So in this video, we're going to focus on what's called the sum of squared errors. This right here, sum of squared errors. And this is a very important concept for linear regression. And just to focus you guys on what we're doing, we got a problem. We got a big problem, right? We're playing a basketball team in our rec league, and they have some mystery player. This mystery player, even worse, used to play for the NBA, and we want to guess how tall is he. We want to get a good estimate for how tall he. In the last video, I was saying estimate. When I wanted to use the noun form estimate, I watched the video over again. I was like, no, but I apologize. Just skip that. Don't worry about that. Just a little grammar problem. It happens. So anyways, we want to get a prediction for how tall this dude may be. Is he going to be some giant? Is he going to be dunking all over us? Is he more of a guard, slasher, shooter type? We want to prepare and help get a game plan. So we want to first get a guess for how tall he may be. And a good guess, whenever we don't have any other information about the person, we only have nothing else to go by. We only have one variable we want to predict, is the heights. We just can get the average heights, right, of a player. But we were able to get the average height of NBA players. And once we got the average height of the NBA player, which was 79 inches or 6.6 feet, 6 foot 6 inches, then we can make a prediction, a pretty simple, dumb prediction, that he's probably 6 foot 6 inches. So we want to do better than that, and that's what we're going to do in the next video. We're going to use more variables to help our prediction. We're going to use what's called independent variables to help predict how tall he is. Right now, we only have one variable, that's height. But if we were able to get other variables like weight, that would be, weight and height are usually associated. So one can help predict the other. Usually we can say how much somebody weighs is a bit dependent on how tall they are. So we can say how tall someone is. It's not really the same way, but here we're trying to predict their height. So the dependent variable is height, and we're trying to predict that based on some independent variables. We are going to talk about that in the next video, but our focus in this video is in the case where we have no other information. We just got heights. And that's what we did. In that situation, the best prediction is just the sum of heights, the average of heights, the mean of heights. And we did that, and we plotted it. Just to show you guys again, I'm going to open up this Python terminal. We're going to cd into our desktop, and as quick as possible, we're going to cd into linear regression folder. We're going to activate our virtual environment. We're going to do ls to remind ourselves that we're using this CSV, this Excel spreadsheet. We're going to enter Python terminal, and then from pandas import pd. We've been using pandas or pd to read our CSV. Import pandas as pd. And then import numpy. We haven't used numpy yet. We're not going to use it in this video, but let's just import it. Import matplotlib.pyplot as plt. And then if we want to read our data, this CSV, we just write the name of it using this pd.read_CSV method, and we write the file path where it's located on your computer relative to the folder we're currently in, linear regression. And relative to that folder, it's just here. So we just write the name of it, .csv, and if we do this, we're going to get an error. I'm going to write enter just to show you guys this error. We get this error that says UTF-8 can't decode it, and we fix it by giving it an encoding, and the encoding is ISO-8859-1, and now it's done. And this is the data right here. So we want to do the data.head to see that we get each player's height, weight, and age, and we can get all their heights. We can get any column we want in this data, just to refresh your memory, by writing any column name. So we can get just player. Let's see, p equals data player. And then P is all the players' names. But what we don't want all the players' names. We want all their heights. So let's write, and just to show you guys again, we want their heights. So data equals heights equals data, and then heights, just like this. And then we have all the heights. The last height is the tallest person, Hashim to beat. The first one is the shortest person, Nate Robinson. So now that we have this, we can plot it very easily. So we can use plt.plot, and we can give it heights, and then this other argument, so say make it a dot. And then afterwards, we can do the y label. So the y label is heights in inches. And then the x label is just number of players. And then why don't we go ahead and print that horizontal line that represents our average. So our average heights dot, let's just do our average equals mean equals heights dot mean. And we can see this is the average height, 79 inches. So why don't we say, we want to plot that horizontal line, and we want it to be given, we do the y equals mean. We don't have to have it, it's also the first argument. So now we have that. Why don't we do plt.show to show our graph. Here it is. Here's each individual data point. Now we're focusing on the sum of squares right here, which is the discrepancy, the difference between the data and the estimation model. So our data, I'm going to close this. Our data is this, right? And our estimation model is just the stupid estimation model when we only have one variable to go with. It's just to guess the mean. So our estimation model tells us our guess for a random player's height for a random mystery player who used to play in the NBA is 79 inches, 6 foot 6 inches. And the actual data comprises of every single NBA player's actual height. So the difference, the discrepancy between our estimation model, this 79 right here, and the actual data is each of these data points and how far they are. So this is all the players. So this is player number 1, player number 2, player number 3, player number 554 or 504, which is Hashim to beat, and he is 86 inches, 87 inches. In this player number 1. So the difference between right here, player number 0, Nate Robinson, and our guess, our estimation model, is 77 is our guess, or 79 is our guess, Nate Robinson is 69, so that's 10. But we want to get the squared difference, right? So 10 times 10 is 100, but we want to get the sum of squared differences. So we want to do that for every single player, and then add it all up, sum them up. So let's do it for one player. So I'm going to quit this right here, and to do it for one player, let's do it Nate difference. Nate difference, and Nate is the last player. Just to show this again, or the first player, just to show data.head, I can show you that he is the first player. He's 69 inches. Nate difference equals, and the mean minus his actual heights. His actual height is 69. So Nate difference equals that. So Nate difference squared equals Nate difference times Nate difference. So Nate difference squared equals 100. Great. Now let's do it for our tallest player. Hashim to beat is 87 inches. So Hashim difference equals mean minus 87. So Hashim difference equals -7, but we want the squared. Hashim difference squared equals Hashim difference times Hashim difference, and that is Hashim difference squared. 62. We want to do this for every player. How to do that? I'm going to show you some special magical Python code that does that for you. It's called list comprehensions. And don't worry if you don't understand how list comprehension works, because we follow the Kalu method for learning new principles. And we don't ask mid-sentence, what does this mean? We just listen to the whole story until we can then guess, okay, we got context for each part of the story we now understand. So that is just a bottom up and not a top down process. That's a learning by inductive reasoning and not deductive reasoning. That's learning by example. Just listen to example, repeating it, and not really wondering what are the rules that govern this example that you're doing. Just redo the example. So just type this code. And this code, what it's going to do is it's going to sum up. First, let's just get all the differences. So differences. So we want to get all, just like we did for Hakeem difference and just like we did for Nate difference, we want to get the difference between a random and height, right? And the difference between a random height and our prediction. So our prediction is our mean, right? 79.9. So height equals, and this is a list comprehension, so let's do mean minus height. Mean minus height for heights in heights. And this for heights in heights, you could figure out what that means. It's just a list comprehension. So differences, and now we have, so len differences, now we have 505 records for the difference between the prediction and the actual height. We can see the last one is 7.9, and that is Hashim difference. That's exactly what we said. And then the first one should be 10, right? So let's just do differences, and let's get the first one, and that should be 10. So we don't want the differences, we want the differences squared. So we want the differences squared, and to do that, we just get num times num for num in differences. And that's going to get the differences squared. So the last one is 62, and if you remember, the last one is Hashim, and Hashim differences squared. I forgot what the name of it, but Hashim differences squared. Hashim differences squared. I forgot what the name of it was, but it was 62 right here. So this is good. So differences squared is what we want, but we don't want just the difference. We just don't want the squared errors. We want the sum of them. So the sum of squared errors, the SSE, equals the sum of every number in here, right? So sum of differences squared, and that gives us our SSE. So why is this important? To answer that, you really have to watch the next video, because this is one of those cases where, as I said in the analogy in my first video about listening to a sentence and not being able to understand what the sentence is until you listen to the entirety of the sentence, this sentence is 2 videos long, and we just understood some components of the entire sentence, of the entire goal, the entire learning goal of this video. So to understand why SSE is important, you really have to compare different models. So first, I want you to watch this video if you have time. This is by a YouTuber called Brandon Foltz, and he teaches you about simple linear regressions, the very basics. And what he says is simple linear regression is really a comparison of 2 models. At the beginning of this video, I talked about one model, the one we've been using and the one we used last video. And that's where the independent variable doesn't exist. Remember, we want to guess this person's height depending on some other factors, like the average, depending on some other stuff, right? But we only have heights. That is a dependent variable. So if there's only one variable, the best prediction for other values is the mean of the dependent variable. So the mean is the average height of all NBA players. That's 79. So that's our best prediction. But there's another model we can use. That's when we have more than one variable. Like, for instance, we have the heights of all NBA players and the weights of all NBA players. These 2 things are generally related. The heavier you are, usually the more you weigh. So in this situation, then we want to find the best fit regression line. And the best fit regression line is going to help us make our prediction model, or as we see here, what did we call it? Our estimation model. So we have one model, which is what we've been using, just one variable, heights. We're going to add a different variable next video, and that's weights as well too. And we're going to ask a different question. We're going to say, given that we know this mystery player's weight, what could we guess his height to be? And that is going to use 2 variables, and we're going to figure that out. But the important thing to know is that whenever you are doing linear regression, what you want to do is minimize, lower the SSE. So our current SSE for our first estimation model is 6,000. we said that this is probably a silly way to guess what his height is. It's the dumb guess. Just guessing without any other information, the average height of a player. So we have this as a SSC. When we add more variables, then we want to hope that this SSE lowers for that particular estimation model. If you don't understand what all this means, I've been talking way too much. I'm going to shush my mouth and tell you guys that you've been doing great for being patient, and the next video is going to make a lot more sense. So stay tuned. In the next video, we're going to do real linear regression using NumPy. It's going to be dope. It's going to be amazing, and all your patience will have paid off. See you guys at the next video. Thank you.